It's the longest bridge of its kind, with a single span leaping almost half a kilometre and a roadway that plunges into a record-setting tunnel. The vision is bold. The challenge is extreme. The plan audacious. It's a bridge that will change the map of Europe. What does it take to build one of the world's mega bridges? In Northern Europe, the Baltic Sea converges with the North Sea at the Øresund Strait, a 16-kilometre wide stretch of water with notoriously lousy weather that separates Denmark and Sweden. The Øresund Strait is a frustrating barrier because each shore has something the other needs. Copenhagen in Denmark needs cheaper housing. Malmö in Sweden needs more jobs. If the two cities could be connected, they could form an economic powerhouse. A bridge would make them one big metropolis. But a bridge has never been possible, until now. The Øresund Bridge is the world's longest cable-stayed bridge. It can carry cars as well as the enormous weight of trains. 1,090 meters of road and rail dangle from 160 cables. 60 meters above the sea. The support towers soar 204 meters into the air, making the Øresund Bridge one of the tallest cement structures in Sweden. The height is the equivalent of a 60-story building. This awesome project officially started in 1991, when the Danes and the Swedes agreed to connect their countries. It was a difficult pact to negotiate, and the subsequent work would only get harder. Companies from both countries formed a consortium to build the bridge together. The consortium's first challenge was to work out how to build a 16-kilometre long bridge. Right from the start, they faced a dangerous setback. At the shoreline on the Danish side was the Copenhagen International Airport, Kastrup. Computer simulations show that building a bridge with high towers would have obstructed air traffic and could have led to tragedy. Building a low bridge would have been safer for air traffic, but then it would have blocked Denmark's ships. Realizing it would be difficult to build over the water, the engineers considered building a 16-kilometre long tunnel under it.
That would be the beautiful solution, build a tunnel from one side to the other, but that would be the expensive solution. So the third solution that we decided was, of course, to build part bridge and then a tunnel where we were getting close to the airport. A bridge would have been easier or cheaper, but would not have been a good idea for the aeroplanes.
But combining a bridge and a tunnel posed a new and serious challenge. How does a tunnel turn into a bridge in the middle of the open sea? The engineers needed to find some dry land where the tunnel could emerge from the water. They needed an island. Unfortunately, no island existed, so they decided to build one from scratch. When it was complete, Denmark had increased in size by 1.3 million square meters. 4 kilometers of tunnel and 4 kilometers of island left 8 kilometers for the bridge to cover. Once again, a low bridge was ruled out because of heavy boat traffic, but there was no airport on the Swedish shore. The engineers could build as high a bridge as they liked, and they needed it to be very high. To clear boat traffic, the bridge would have to stand at least 60 meters above the water, and the center span would need to be more than 450 meters long. To meet these challenges with the best possible bridge, the consortium held a design competition. One of the most spectacular proposals was to build the largest arch bridge in the world.
I think you don't really get an idea of the magnitude of this arch. You might get it from the ship going underneath, but it really is big. It would be a monument of some kind.
But arch bridges have an Achilles heel. As the arch sweeps down towards the water, the clearance for large ships decreases, eventually to nothing.
You always run the risk that a ship could get in there, and therefore you have the risk of hitting the bottom part of the arch, and then the whole thing collapses.
Unable to build an arch, they then looked at building a suspension bridge. Suspension bridge technology enables the longest spans of any design. Two enormous cables stretch the entire length of the bridge, with shorter cables dangling down to hold the roadway. But connecting cables to more cables makes suspension bridges very flexible, and trains can't operate effectively on tracks that bend under their weight.
And railway traffic is so heavy that if you have a suspension bridge, you will find, if you look at it from the side, that the train will always go up a little bulge. It will always going uphill all the time.
Suspension and arch were both ruled out. The engineers then turned to the one design that met all their criteria: a cable-stayed bridge. Its structure is rigid enough for heavy train traffic because the support cables attach directly to fixed towers. And there's a bonus. Cable-stayed bridges are cheaper to build than suspension bridges. Not having the two enormous main cables saves tons of steel. The decision was made. The best design to meet all the Øresund's needs was a towering two-level cable-stayed bridge with a four-lane road on top and a high-speed railroad underneath. It would be a monumental structure, the crowning achievement in the 16-kilometer Øresund link. But the clock was ticking. The agreement between Sweden and Denmark stated that the link must be completed in 5 years. That was 5 years in which to build a man-made island, a record-setting bridge, and the biggest tunnel of its kind. The first priority was the island. This was one of the most critical deadlines. It had to be ready in 14 months. Work began on the 17th of August 1995, when the first of billions of rocks was placed in the middle of the strait. This stone pile would eventually form a 4-kilometer long island, where once there was only water. The first step was to lay the perimeter. Large quarried stones were brought in from Sweden, 1.8 billion kilograms of them. To stay on schedule, material was constantly being brought here, with 16 barges delivering 18 million kilograms a day. Each load was carefully placed using GPS to create a perimeter 12 kilometers long. Then it had to be filled. This was an enormous task, requiring millions of cubic meters of material. And Denmark and Sweden got that material from the bottom of the sea. Phase 2 was dredging. Here the engineers came up with an ingenious win-win plan. Construction crews needed to dredge anyway to prepare for the bridge and tunnel. Now they had a place to put all the rubble. To stay on schedule, crews had to dredge an average of 11.5 million cubic meters every day. This job required the biggest, most powerful dipper dredger in the world, the Chicago. Its scoop bucket is big enough to hold a minivan. Just one pass of its giant shovel can dig up 22 cubic meters of seabed. Its floating platform is so big that parts of the Baltic Sea weren't deep enough for it. It had to dredge a lane for itself just to navigate the construction sites. But digging was only the first part of this project. Crews then had to transport this astonishing amount of dredged earth. An armada of 50 vessels was assembled. For the pilots, it was dangerous work. It took expert skill to navigate the huge loads, fighting against strong currents, extreme weather, and shallow waters. The single biggest dredging job was the trench for the submerged tunnel. 11 meters deep and 46 meters wide, for 4 kilometers. A total of 2 million cubic meters of seabed. It would have been hard enough to dredge if they were just dealing with mud and stones, but they weren't. 90% was an ultra-hard rock called Copenhagen limestone. Even the Chicago couldn't dent it. So the builders called in one of the most powerful cutter suction dredgers in the world, the caster. The caster's business end is a mega drill bit with 60 cutting teeth, each weighing over 20 kilograms. It's sometimes known as the spinning cone of death. But even with all this firepower, the Copenhagen limestone didn't surrender easily. It destroyed 200 teeth a day. 52,000 were replaced in total. The caster is more than an overgrown drill. It also acts as a vacuum cleaner. As it chipped away the limestone, it sucked up the debris. Giant pumps then forced the stones and water through 4 kilometers of pipeline, all the way to the island. The shards of limestone were so abrasive, they eroded the inside of the pipe. And moving all this rock and mud involved an additional challenge: protecting the environment. The environment is especially vulnerable in the shallow Øresund Strait. The biggest threat is from plumes of debris. Clouds like these can kill huge areas of the seagrass that feeds and shelters marine life. For both Denmark and Sweden, harming the environment was a deal breaker. They made a pact that if more than 5% of debris was spilled, all dredging must stop. A decision that would put the entire project at risk. 5% spill doesn't sound like much, but it equates to 340,000 cubic meters of misplaced rock. Avoiding spills required a balance of speed and caution, but the dredging workers succeeded in working within their environmental limits. But they were about to face another danger, one that would threaten their own lives. The 25th of November 1995 was the 30th day of dredging for the Øresund link. Digging up the 7 million cubic meters of seabed seemed to be a fairly straightforward assignment, and the crew thought everything was going smoothly. But dredging had just become the most dangerous part of the entire project. Workers didn't know it, but they were just centimeters away from death. The problem started when the Chicago accidentally scooped up a dangerous payload, a bomb that was ready to explode. It then dumped it onto a barge covered in mud. Nobody knew it was there. If anything had bumped its detonator, 36 kilograms of TNT would have blasted the barge and crew to pieces. How it ended up here is a story that dates back 60 years. In May 1945, Denmark was celebrating the end of World War II. The British Royal Air Force put on an air show over Copenhagen harbour with live bombs. Some sank without exploding, and now, 6 decades later, they're more deadly than ever.
Even though the bomb is maybe 50, 60 years old, it can still work as designed. So that's why it's dangerous, always. If the bomb has gone through some corrosion and there has been some deterioration of the explosive, it may have become even more sensitive, and in that case, even more dangerous.
Equipment inched closer to the bomb. Then, just in time, someone on the dredging team spotted it. The Royal Danish Navy was called in to remove, defuse, and explode the bomb. These bomb experts knew better than anyone that the outcome could have been tragic.
If they hit the bomb with their dredgers or with their buckets or whatever, and it went off, somebody had been killed.
It was a narrow escape for the crew and the schedule. With the bombs gone, dredging resumed. But the relief was short-lived. Soon, more bombs were discovered. Luckily, no one was injured, but the schedule suffered huge setbacks. Now, no area could be dredged until it had been swept for bombs. All 16 were removed and destroyed. Being safe was more important than being on schedule. Long before the bombs had been discovered, and even before a dredger had dipped its first bucket, the Øresund engineers knew they faced a unique set of very difficult challenges here. The water separating Denmark from Sweden was 16 kilometers across, but the cultural gap between the nations was much larger. They were two very different countries, with different languages, currencies, and ways of doing just about everything. Cars didn't even drive on the same side of the road until the 1950s. And trains still don't, passing on the right in Denmark, but on the left in Sweden. They also run on different electrical voltages and use different signals and radio frequencies. None of this had mattered before, because the countries had never been connected. But now it was a puzzle that needed to be solved before the bridge could open. Engineers needed to design a computerized Rosetta Stone so that the different train computers could communicate. They also needed to create a standardized wording so that all train operators would understand spoken instructions. And designers had to invent electrical equipment that would switch trains from 25,000 volts to 15,000 volts on the fly. The solutions were so complicated that every new train would need to be tested without passengers before it could use the Øresund link. But there was also a problem with emergencies. Firefighting equipment in one country didn't fit equipment in the other. The best solution was to put both couplings on every water hydrant. Every little detail required collaboration. The countries didn't even use the same name for the strait, The word Øresund is a mixture of the Danish and Swedish versions. While some of the team worked on a name for the link, others continued to work on how in the world to build it. The plans called for a submersible tunnel bigger than any ever made before. The first step was to construct a factory to make tunnel parts. The idea was to make the tunnel in 20 segments, then assemble them in the trench. Even the segments would break world records for size. They were 175 meters long, 38 meters wide, and 8.5 meters high, with 2 tubes for traffic, 2 for rail, and 1 for emergency escape. One enormous segment had to be created every month for 20 months. In Denmark, the tunnel construction began with 40 million kilograms of reinforced steel bars. These were bent and welded into a huge steel cage, then slid into an enormous mold. Then the massive framework was encased in more than 7.5 trillion litres of concrete. Of all the monstrously large parts of the Øresund link, the tunnel elements were by far the biggest. They were nearly the length of 2 football fields and as high as a 3-story house. A single piece weighed an astronomical 55 million kilograms. Moving them was an enormous and dangerous challenge, one that triggered the most catastrophic accident of the entire project. Each tunnel segment weighed more than the equivalent of 24 space shuttles. Between them, they contained enough concrete to build a pavement around the Earth twice. No machine in the world could lift one into the air and put it into place. And these engineers had to get each 55 million kilogram piece off dry land and into the middle of the Øresund Strait. The answer was to turn them into rafts and sail them. First, any holes were plugged with giant steel plates, each weighing more than 3,000 kilograms. These enabled the gigantic concrete structures to float, but there was still no way to transport them to the water. So an ingenious lock system was built to bring the water to them. The end of the assembly line was surrounded on 3 sides by dikes. The 4th was closed by a huge movable wall, and the basin was flooded to more than 9 meters above sea level. It took 100 million liters of water. Even when afloat, 4 23,000 kilogram winches were required to move each segment, and 2 more winches to steer it to the deep end of the basin. When the water returned to sea level, the segment was ready to head out. Then, when it was over the trench, there was a new challenge: sinking it. Forcing a raft this big underwater was not an easy task. The trick they used was ballast. Water was pumped into special tanks very slowly and evenly to keep the segment horizontal. 4 massive cables helped guide its descent. Precision was paramount, so it could be accurately connected to the rest of the tunnel. Winch operators used GPS and depth gauges to make sure they kept on target. The margin of error was less than 1¼ centimeters in any direction. Divers installed a temporary frame to help guide it. Then, when it reached the seabed, winch operators pulled it tight against the previous segment. Any seawater trapped between the segments was pumped out. The steel panels were removed, and to keep the tunnel from ever floating again, concrete, almost a meter thick, was poured the entire length of the roadway, then boulders piled on top. The system worked flawlessly for the first 12 tunnel segments, but the 13th still got special handling. It was officially numbered 12A for superstitious reasons, but unfortunately renaming it wasn't enough. On Tuesday the 4th of August 1998, wind and current conditions in the channel were perfect. The tow-out of the new tunnel element started uneventfully. By midday, element 12A had been guided into position. At 3:30, pumps added ballast, slowly sinking the unit beneath the waves. Then, suddenly, something went very wrong. The segment started to tilt, and then collapsed. A huge explosion of water blasted 30 meters into the air. The segment plunged to the bottom. Crews on the pontoons shut down all power, fearing they'd be electrocuted. It was hours before they figured out what had gone wrong. The verdict was human error. A steel plate hadn't been sealed correctly. Water pressure had forced it open and flooded the segment. The winches weren't able to hold the added weight. Luckily, no one was injured. But what about tunnel segment 12A? Extensive testing confirmed it was still usable, but valuable time had been lost. Øresund's builders could have chosen a different method to build their tunnel. They could have bored a tube under the seabed. This is what Denmark did 2 hours away from Copenhagen, where rail and road needed to cross a channel called the Great Belt. This was the site of a disaster far worse than the Øresund's. To dig the two train tunnels, they brought in 4 enormous boring machines, each 90 meters long. The front end is a drilling head weighing over 100 million kilograms and measuring 7 meters across. The cutting head chews up soil and boulders. An auger shuttles the ground bits to a conveyor belt, and they're eventually dumped on a small train. As each tunnel boring machine worked its way underground, it also installed pre-made wall segments, 62,000 of them. The problem with boring was that the ground could be unpredictable, and this was how disaster struck the Great Belt. A boring machine hit a water pocket. At first, water began to drip in. Then it started to pour. A special safety hatch should have contained the flood, but it had been left open. Water flooded one tunnel, crossed through the emergency tunnels, and flooded the second. It took a year to get the project back on track. The tunnel here differed from the Øresund's in another way. It went right across the channel, so heavy trains wouldn't have to use a bridge at all. This gave engineers more design options than they had at the Øresund. They were able to build a suspension bridge, and they did so in a big way. The second largest in the world, spanning nearly 2,700 meters. The towers reach up 250 meters, almost 30 meters taller than the towers on the Golden Gate Bridge in San Francisco. Unlike the Øresund, this bridge's structure depends on 2 main cables draped over the towers. These monster cables are almost a meter thick and around 3 kilometers long. The main cables are actually made up of over 18,000 wires, each thinner than a pencil. They're not twisted together, instead they're stretched next to each other and bundled. The finished cables weigh over 9.5 million kilograms each. The trick to making a suspension bridge is anchoring each end of the cable. For the Great Belt Bridge, the anchor blocks were enormous, little islands unto themselves. Each weighed more than 300 million kilograms. Cable-stayed bridges like the Øresund don't have anything like this. Anchor blocks are just used for suspension bridges. But the cable can't just be buried in the concrete. It would pull right out. The load has to be spread over a large area. So as the cable enters the anchor block, the wires branch out into smaller and smaller clusters. By the time the Great Belt cables reach concrete, their load is spread over 64 square meters. It's easy to see the cable's flexibility in the anchor block.
It would take a little time but it will actually start to move. Now it's moving a little, 3 or 4 millimeters, but it's moving all the way from the top and down to the anchor plate.
This was exactly the kind of flexibility that the Øresund bridge needed to avoid. It had to be rigid in order to carry the tremendous weight of car and rail traffic. And it needed awesome engineering if it was going to break world records. Having to build the bridge section this high and this huge created the biggest challenge of the entire Øresund project. Engineers were hurtling full speed towards the July 2000 deadline. The last stones had been placed on the artificial island. The tunnel elements had been sunk. Now it was time to build the world's longest cable-stayed bridge for car and rail. Construction began with the towers. At 60 stories, they would be by far the highest freestanding double-legged bridge towers in the world. 2 giant legs would be connected by a massive crossbeam just below the roadway. Above the deck would be open space. There were 2 reasons for this lack of crossbeam above the road. It kept the bridge design looking clean, but it was also in case of a plane crash. If this computer-animated disaster were ever to become reality, freestanding towers would help the bridge survive. Without a crossbeam above the road, the towers would be more flexible. In the event of a crash, less of the impact would be transmitted to the rest of the bridge, and it would stand a better chance of survival. The building of the towers started on land. Like the tunnel segments, the foundations were made in a dry dock. They were enormous, the base of each covering 1,500 square meters, enough land for a house, garage, and garden. Their dead weight was over 18 million kilograms. This was a lot lighter than the tunnel segments, but moving them was much trickier. They were 22 meters high. The Øresund Strait was only 7.5 meters deep, so they couldn't be floated like a raft. They had to be carried. No vessel existed that could do this, so the Øresund engineers built one. They started with 2 immense barges, then connected them at both ends to create a kind of catamaran. Then the dry dock was flooded, so the catamaran could sail over the foundation. It took 5 enormous tugs to tow this contraption into the channel. At the bridge line, the foundation was lowered into a pit that had already been dredged into the seabed. GPS helped guide it to within 8 centimeters of its target. At this stage, the foundation stuck out of the water by just 3 meters. Soon each stump would grow another 180. Each embryonic tower became its own self-contained construction site, outfitted with enough equipment for a small factory. The 2 legs for one tower climbed into the sky in 4-meter sections. One always stayed 12 meters ahead of the other, so the massive cranes didn't get tangled. When the towers reached 44 meters, it was time to add the crossbeam. Then, at about 80 meters up, a steel box to hold the stay cables was integrated into the leg. Another box was added every 12 meters. From the outside, the towers look solid. But in fact, they're packed with equipment, including a lift. A hatch in the top of the tower reveals the penthouse view. At the same time as the towers were being built in the middle of the Øresund Strait, the double-decked spans were being assembled at shore. They were immense steel and concrete boxes, about 140 meters long and 23 meters wide. The top would be a 4-lane highway, while the trains would go inside. The designers decided to put the train tracks in a special cement trough. If a train was to derail, they hoped this liner would keep the train on the bridge. The bottom of the spans may look solid, but like the towers, they're hollow. And they too housed equipment critical to the bridge. The bridge contained a total of 18 million kilograms of steel, and steel has a mortal enemy: rust. Rust could potentially destroy the bridge from the inside out. Paint can add protection, but it was not economical to paint so much surface area. So instead, the Øresund Bridge was constructed to contain a vast system of dehumidifiers. These keep the air inside below 60% relative humidity, and no moisture means no rust. Regulations required crews to inspect every part of the bridge. This was obviously a prudent measure, but a big challenge, because the underbelly of the bridge was 60 meters above water. Even on the road, workers had to be protected without interrupting car and train traffic. Luckily, the Øresund engineers had planned ahead. Hanging under the bridge is a spectacular motorized gantry. The Øresund link has one of the few gantries in the world that can run the entire length of the bridge. Most gantries would be stopped at the bridge towers. But this gantry pivots to squeeze between the supports. On the other side of the tower, it spins again and continues on its way. Once the crew is in the right place, the Øresund's gantry works like a gigantic Swiss Army knife, packed with exotic contraptions. A hydraulic arm can carry a worker outside the trusses, up and over the roadway. The access is phenomenal and, most importantly, doesn't interrupt the flow of train and car traffic. Hanging so far above the water, the arm gives access to equipment like this device, created especially for the Øresund Bridge. It's a damper to reduce cable vibrations that could potentially shorten the life of a bridge by decades. The gantry has another gadget used to inspect the towers. This hanging bucket can lower workers 60 meters, right down to the waterline, where they can check the concrete for cracks and even change the light bulbs that guide ships through the navigation channels. From the gantry, it's easy to see that the deck was assembled from pieces. It's less obvious how the pieces got here. The enormous segments were pre-assembled several kilometers away on shore. The good news was that they only weighed 5.5 million kilograms, not 18 million like the foundations, or 55 million like the tunnel elements. The bad news was that the tunnel and foundations were lowered into place. The bridge spans needed to be lifted, 60 meters up, and then held dangling in the air. By any measure, the Øresund link was one of the most ambitious engineering projects of the 20th century. The contractors built from scratch an artificial island 9 kilometers around. They ground through 4 kilometers of ultra-hard Copenhagen limestone. And and they pieced together the world's largest submerged tunnel. Now, with just 1 year left, it was time to begin the last and most spectacular stage of construction. Finally, the bridge would start looking like a bridge. All the planning and all the calculations would be put to the test as the main span was put into place. It had to be high enough for ships to pass under and strong enough to carry speeding trains and cars. No one had ever built a bridge like it. What was required was the largest floating crane on Earth, capable of lifting more than 7 million kilograms, the equivalent of 30 Boeing 737s. It was called the Swan, and this was her moment of glory. The Swan had to use 75% of her total strength to lift each span. The highest span went right next to the tower. Then crews attached cables. The first cable was 50 meters long, and each new cable would be longer than the one before it. The longest would be over 260 meters. The Swan brought in another span. The roadway cantilevered further from the tower and closer to a world-size record. This was the most vulnerable time for the bridge. Temporary scaffolding helped, but the bridge wouldn't be up to full strength until all the pieces were in place. Wind and storms could be disastrous. On the 14th of August 1999, the Swan installed the final roadway span on the bridge. Denmark and Sweden were connected for the first time. Denmark's Prince Frederik and Sweden's Crown Princess Victoria met at their first ever border crossing. For 9 years, the construction deadline had loomed over everything and everyone involved in creating the Øresund link. Finally, on the 1st of July 2000 at 11 p.m., the Øresund link officially opened for business, on time and on budget. The bridge may have been open, but the challenges didn't stop there. Now it had to pay back every penny spent on it, one toll at a time. The official budget for the bridge, tunnel and island was close to $3 billion, and the expenses would never stop. There will always be maintenance. Not long after the link opened, engineers discovered a problem with the guardrails. The bolts were corroding. One bolt was not much of a problem, but there were 16,000 of them, and if they failed, a minor fender bender could turn into a death plunge. Crews had to act quickly to prevent the bolts from rusting through. It was a big job, but it was better than waiting now and having to replace the bolts later. That would have required tearing up the concrete. Stopping the corrosion started with removing the nuts and blasting the bolts clean. To keep out moisture, crews coated the bolts with gel and used better fitting washers. Maintenance and everything else that happens on the bridge is monitored in Sweden from a building near the toll plaza. Hidden inside is a high-tech command center.
Traffic center, Arne. Okay, he's coming to work with
30,000 points of information from the bridge feed into the control room computers. Operators constantly monitor safety. There are 256 cameras on the link, too many for operators to monitor, so a computer helps. It's able to recognize stopped cars and cars going the wrong way. When it spots trouble, it alerts the operators and shows them the appropriate camera. Operators can also manually control the cameras, which have incredible zooms. One of the Øresund link's pleasant surprises can't be seen from the control room. It's underwater. The 51 bridge piers have had an unexpected environmental impact. They've become artificial reefs, covered in mussels and plants, providing food and shelter for sea creatures. Environmentalists who were originally against the Øresund project now document an explosion of life here. Creating a fixed link across 16 kilometers of the Øresund Strait had been a dream for generations. It was a monumental engineering effort, pushing technology to the absolute limit and establishing new world records, from the coast of Denmark to the coast of Sweden. The largest submerged concrete tunnel in the world. The world's longest double-decked bridge for car and rail traffic. And the tallest freestanding double-legged pylons on any bridge anywhere in the world. In its first 5 years of operation, more than 44 million people crossed the Øresund link, going to new jobs, to new homes, or just exploring. The Øresund link changed the map of Europe, successfully bringing 2 cities, 2 countries, and an entire continent closer together. It stands as one of the world's mega bridges.